Alright, so today we are starting chapter 2 in section 1 called the instantaneous rate of change. So the first thing we're going to do is recall the average rate of change between 2 points. The average rate of change between 2 points, which we learned about in chapter 1. Alright. Well, that's our change in y over change in x. Remember, these little triangles are delta. So delta y over delta x. All right. From between x is equal to a and x is equal to b. So those are between our 2 points. So that's our function at the value b minus our function at the value of a over b minus a. So that's our average rate of change between 2 points. So our first example asks us to try to find the slope of f of x is equal to x cubed at x is equal to 2 by applying the average rate of change formula with a is equal to 2 and b is equal to 2. Alright, so if we go ahead and set this up, we have delta y over delta x. Well, that's going to be our f of b minus f of a over b minus a. And we have a and b right here. So f of 2 minus f of 2 over 2 minus 2. Alright, we could keep going. The function at 2 is going to be 2 cubed minus 2 cubed over 2 minus 2. Do we see any red flags here? I'm specifically looking at this 2 minus 2 in our denominator. Alright, here we would be dividing by 0, which we know causes all sorts of mayhem, the world implodes, that sort of thing, right? So we can't be dividing by 0. So automatically we have an issue with trying to find this average rate of change at 1 point. Alright. So, is there a way that we could get close to what we are looking for? Looking for. And take a second, what are we even looking for? We're looking for the rate of change instead of between 2 points at exactly 1 point. So we are looking for the average rate of change at exactly 1 point. Alright, so in other words, our interval, so our a to b interval, well, it has a length of 0 because a is equal to b. Alright, so it's going to become a to a interval or something like that. So this is our instantaneous rate of change. So the speed that something is changing, the rate of change at exactly 1 point. So over an interval so small, it doesn't even exist. It's a 0 length interval. Right? So, is there a way we could get close to what we are looking for? Well, let's go ahead and work through example 2 to see if we can answer that question. Alright, so example 2 asks us to find the average rate of change between different points listed here. This is the same function as before, x cubed. Alright, and here we have between 2 and 3. So, a is 2, b is 3. So we have f of 3 minus f of 2 over 3 minus 2. Well, f of 3 is 3 cubed minus 2 cubed, over 3 minus 2. Well, 3 minus 2 is just 1. All right. And I went ahead and plugged this into a calculator, and we get 19. Okay, so we've found the average rate of change between 2 and 3. It's 19. All right, now for part B, we're asked to find the average rate of change between 2 and 2.1. All right, it doesn't always need to be whole numbers. It just makes calculations a little bit simpler. All right, but let's look at between 2 and 2.1. So we have f of 2.1 minus f of 2 over 2.1 minus 2. So we have 2.1 cubed minus 2 cubed over 2.1 minus 2. Well, that's just 0.1, right? So we get 1.26 over 0.1, which simplifies to 12.61. Okay, let's go ahead and look at part C. So x is equal to 2 and x is equal to 2.01. So if we notice what's happening here, the length of our intervals is getting smaller or shorter, however you like to think of it. Alright, so let's keep going. We have f of b, which is 2.01 minus f of 2 over 2.01 minus 2. So now we'll have 2.01 cubed minus 2 cubed over, well, 2.01 minus 2, that's going to give us 0.01. Alright, which will come out to be 12.06. And let's go once more. We have f of 2.001 minus f of 2 over 2.001 minus 2. So we have 2.001 cubed minus 2 cubed over 0.001, which gives us 12.006. Alright, so if we notice what was happening, our interval was getting smaller and smaller. And we were just discussing, is there a way we could estimate or we could get close to an interval length of 0? So what we're doing is we're making the intervals as small as possible, and we could keep going smaller if we wanted to get closer and closer to that actual value. So based on these results, what is a good estimate for the slope, which remember is our rate of change, same thing as slope, okay, at x is equal to 2 for the function x cubed? Well, if we notice our answers here, we started off, the rate of change was 19 over the biggest interval, and then our rate of change went to 12.6, 12.06, 12.006. So it looks like we're honing in, getting closer and closer to the value 12. And if we kept going, maybe we'd get 12.0006, right? And we're getting closer and closer to 12. So a good estimate for the slope of x cubed at x is equal to 2 would be 12. All right? If we could actually calculate it at the exact moment, it looks like it's going to be 12. So that's what we're asked here. All right, so let's go ahead and officially define our instantaneous rate of change. All right, so the instantaneous, there's an S in there, instantaneous rate of change. Instantaneous rate of change of a function f at a point A is also called just the rate of change of f at A. All right. I'll put these in commas here. So the instantaneous rate of change of f at A, also called the rate of change at f of A, is the average value is the average rate, of change of f as the interval around A gets smaller and smaller. All right, so this is also the slope of f at A. All different ways to say the same thing, okay? I'll say also called. So this was our 2 to 3, and then, or 3 to 2, and then 2.1 to 2, and 2.01. So our interval is getting smaller and smaller. All right, so that could be our delta x, right? So our change in x is smaller and smaller and almost 0. We just can't actually get to 0 because we can't be dividing by 0. Okay? So, example 3, we have the quantity in milligrams of a drug in the blood at time t in minutes is given by g of t is equal to 25 times 0.8 raised to the t power. We're asked to estimate the rate of change of this quantity at t is equal to 3 minutes and interpret the answer. Okay? So, based on our previous calculations, we know that we can estimate a pretty good rate of change by doing a really small interval. All right, so we're going to estimate between 3.001 and 3. All right, this was our last option for the previous question, so we're going to go with this. Okay? So we know we're going to need f, or in this case, g. We have delta g over delta t is really what we have going on here. So we have g of 3.001 minus g of 3 over 3.001 minus 3. All right. So if we want to go ahead and calculate these values over here on the side, so we have g of 3.001, well, that's going to be 25 times 0.8 raised to the 3.001. All right, which is going to give us 12.797, okay, and g of 3 is going to give us 25 times 0.8 cubed, which will be 12.8. All right, so if we come back over here to our large fraction, we have 12.797 minus 12.8 over 3.001 minus 3. Well, that's going to give us negative 0.003 over 0.001, which simplifies to negative 3. All right, so the first thing that we notice is our rate of change is negative. So when we want to interpret our answer, a negative rate of change means something is decreasing, right? It's going down, it's decreasing. So in this case, it would be, instead of something, means the quantity of the drug that's in the blood system is decreasing, all right, at this rate of 3 milligrams, all right? But instead of over a whole minute, it's over a very, very, very small time period, almost instantly. You can think of this as when you're driving down the highway and your speedometer is telling you you're going exactly 67 miles an hour, okay? And that is the exact speed you're going at that exact moment. So it's not over a distance, it's instantly. All right, so the instantaneous rate of change is so important that we give it its own name. We call it the derivative. So the derivative of a function f at a point A, which we write f prime of A. Sorry, I'll fix those parentheses. F prime of A. All right. And is read as what I just said, f prime of A. All right. Is the instantaneous rate of change of f at the point A. All right, and just to keep everything straight, the instantaneous rate of change, so of f at t is equal to A, is the same thing as the slope of f at t is equal to A, which again is the same thing as f prime of A. So these are all referring to the same thing, but now we have a lot shorter way to write it, this f prime of A. All right, so example 4, we're going to use a calculator to graph f of x is equal to x squared, which we know was just an upwards facing parabola, right? So I'm just going to go ahead and write y is equal to x squared for graphing purposes, okay? And get my computer to graph it for us here. Go ahead and insert this on the page. I don't want it to cover up the question though. All right, so there's our upwards facing parabola. F of x is equal to x squared. Let's see, I'll use some brighter colors here. So this is x, and this is f of x. All right, so we're supposed to use this graph to determine each of the following quantities, whether they're positive, negative, or 0. All right, so the first one is f prime of 1. So f prime of 1 looks like it occurs somewhere over here, right? Okay, and we're going to need a line for that, because this is the slope of the line, right? At that point. The instantaneous rate of change, the slope at that point. So based on what we know about slopes, is this positive, negative, or 0? This one is positive. All right, how about f of negative 1? Well, negative 1 is over here at this point. So this is a negative slope. How about positive 2? I'll zoom in a little bit more so we can see this better. So if this was 1, this is going to be 2 over here. So our line will look something like this. Again, it's positive. Let's jump to the last one, f of negative 2. We can go ahead and say that one's going to be negative because it's this one over here, right? Now how about f of 0? 0 is the vertex. So the line tangent, and tangent just means next to, okay? The line tangent to this point is the x-axis, all right? And this has a slope of 0. Remember, you can ski on this slope, it's just difficult. So this is the slope of 0. All right, so then we're asked in part B, which is larger, f prime of 1 or f prime of 2? So again, which slope is larger? Or where is our function's rate of change faster or greater? Okay, so 1 or 2. So let's look down here again. I'll do a different color. Let's do blue. So our tangent line at 1, if this is 1, and our tangent line at 2, again, these are not super to scale, well, which one has a steeper slope? Hopefully we see that the yellow line has the steeper slope, so that would be at x is equal to 2. So f prime of 2 is larger. Similarly, we can look at f prime of negative 2 and f prime of negative 1. So f prime of negative 1 is over here, where we had a negative slope, and then f prime of negative 2, where we have a negative slope, but it's still steeper than the f prime of negative 1, right? So we will have f prime of negative 2 is the steeper slope. All right, so we get to our last definition for today, the instantaneous velocity. So the instantaneous forgot a whole syllable there, velocity. So the instantaneous velocity of an object at the time t is the average velocity of the object as the interval around t gets smaller and smaller. All right, so this is similar to our previous definitions, but this case we're specifically talking about speed, which we call velocity. All right, so example 5. Suppose we throw a grapefruit straight upwards into the air. The following table gives the height, which is y, at the time t. All right, so let's go ahead and look at this table. It looks like we have 6 seconds worth of data. Time is in seconds. All right, so we have, well, 7 seconds. We're starting at 0. All right, so at time is equal to 0, the grapefruit is 6 feet off the ground. All right, because y is the height. So most likely, this person is holding the grapefruit at about 6 feet high. And then, so that's where it's starting. It's not starting at the ground. So they're holding the grapefruit and they're going to throw it up, okay? Straight upwards into the air. So, first part, A, why is it impossible to exactly determine the instantaneous velocity of the grapefruit at t is equal to 1? Only using this table. So again, the velocity is how quickly position is changing. All right, that's why we're looking at the height. And we typically deal with position functions as s of t, which is why we have that here. All right. So, well, why is it exactly or impossible to exactly determine the instantaneous velocity? Well, we don't have the function, right? All we have is this set of data in our table. And we learned earlier that we can't divide by 0. So that's the first problem. Can't divide by 0. So that's why we can't exactly determine it. Can we estimate it? All right. Well, again, in our previous examples, we were looking at smaller and smaller and smaller intervals. Here, do we have a small enough interval in our table that we think we could come up with a good estimate for the instantaneous velocity? We don't really. So our second issue is not a number or no data close enough to t is equal to 1 to give a good estimate. All right, so although we don't have a ton of good data, we still want to try our best to estimate the instantaneous velocity of this grapefruit. All right, so what can we do based on what we know? Well, we can find the average velocity between 0 and 1, and then again between 1 and 2. And we know that our instantaneous velocity needs to be somewhere in between those, right? So let's go ahead and look at between 0 and 1. So we need s of 1 minus s of 0 over 1 minus 0. That's going to give us, well, s of 1 is 90. S of 0 is 6. 1 minus 0, well, that's 1. Okay? So we have 84 is our average velocity between 0 and 1. All right, let's go ahead and look at between 1 and 2. So we need s of 2 minus s of 1 over 2 minus 1. S of 2 is 142, and S of 1 is 90. Again, over 2 minus 1, which is just 1. So we get 52. Between seconds 1 and 2. All right, so we know that our instantaneous velocity at t is equal to 1 needs to be between, so instantaneous velocity at t is equal to 1 must be between 84 and 52. All right, so if we're trying our best to estimate this, I mean, we can either pick a number, right, but maybe with some more method behind it. We could say, well, let's just go ahead and split the difference. I feel like that would be a decent approximation, right? These are just approximations. We can't exactly determine it with the knowledge that we are given just yet. All right, so let's see. If we take 84 minus 52, the difference is 32. All right. And so if we want to split the difference, that's half of 32, which is 16. So our estimate of the rate of change, or for the rate of change, for the instantaneous velocity rather, at t is equal to 1 is going to be either 84 minus 16 or 52 plus 16, right? That's still the middle. So that's where we're going to get 68. All right, which is the middle between 84 and 52. All right, so that's all we have for section 2.1. Tune in for section 2.2 next.